Video we're going to be solving an exponential equation. We have 3 to the power x squared times 9 to the power x equals 27 to the power square root of x. We're going to be solving this equation for x. We're going to be looking at real solutions as well as non-real solutions if there are any. So we're going to be finding all the solutions. Let's go ahead and manipulate this equation so we can write everything as a power of 3. So to write everything as a power of 3, I'm going to do the following. I'll write the 9 as 3 to the second power, 27 as 3 to the third power. And then we're going to multiply the exponents, 3 to the x squared, 3 to the power 2x, and 3 to the power 3 times square root of x. Now on the left hand side, we have a product. So when you multiply two powers with the same base, you add the exponents, right? That's the rule. So if you have a to the power m times a to the power n, it just becomes a to the power m plus n. So by using that rule, we can write 3 to the power x squared plus 2x. And that is equal to 3 to the power 3 square root of x. Now, we have the same base on both sides, so we can basically say that the exponents are equal. By the way, I forgot to tell you, I'm going to show you a graph at the end. So let's go ahead and set these equal to each other, and we get an interesting equation. What kind of equation do we have? We have a radical equation because we have square root of x. So we're going to use substitution. Let's go ahead and set square root of x equal to u. And also don't forget that u must be greater than or equal to 0. But think about it. Can u be 0? It could be. So let's just say for now that u must be greater than or equal to 0. Of course, this implies that x is also greater than or equal to 0. Great. Now, under those conditions, we're going to solve this equation by substitution. If square root of x is u, then x must be u squared, and x squared can be written as u to the fourth power. Just keep squaring both sides. Okay? Now we can go ahead and replace x squared with u to the fourth power, and x with u squared, so this becomes 2u squared, not 2u. It's not happy birthday. But anyways, it's still good. And 3 times the square root of x is just going to be 3u. And then we're going to go ahead and put everything on the same side. When you're solving an equation, do not cancel out terms. Always put everything on the same side, set it equal to 0, and then factor. So that's what we're going to do next. We're going to go ahead and factor this equation. Take out a u, and you end up with u cubed plus 2u, yeah, finally we got the birthday song, minus 3 equals 0. Okay, so now we got an equation. It was a quartic, but it's easily factorable. And guess what? U equals 0 obviously is going to be a solution from here, right? We can safely say that, yeah, u equals 0 works, but we're going to check that out. And then the second equation, the cubic, has a special property. Remember, we talked about this many times before. The first thing you check in a polynomial is the sum of the coefficients. If you add these up, 1 plus 2 minus 3 is equal to 0. That just means that u equals 1 is a solution. Okay? So u equals 1 is a valid solution. It's also nice because it allows us to reduce the degree by using long division or factoring. So I'm going to write this cubic as, since u equals 1 is a solution, that implies by factor theorem, u minus 1 is a factor. Make sense? Okay. So since u minus 1 is a factor, I can go ahead and write u cubed plus 2u minus 3 as u cubed minus u squared, and then plus u squared, so that cancels out. And then I have 2u, but I do need a minus u here to make u minus 1 a factor. And then I have to make up by adding 3u because I have 2u, and then minus 3 will finish it up. Notice that this is factorable by grouping, and of course, because u minus 1 is a factor, we knew that, right? So now you can go ahead and write this as u squared times u minus 1, u times u minus 1, and 3 times u minus 1. Great, now our equation was almost factored. Let's go ahead and finish it up. So we can take out u minus 1 as a common factor, and then second factor is going to be u squared plus u plus 3. So the cubic was factored into a linear and a quadratic, the product of two polynomials, which is nice because now we can set this equal to 0 and find more solutions. We already know u equals 1 is a solution, so this one checks that. But let's go ahead and focus on the second equation, the quadratic. This quadratic, unfortunately, or should I say fortunately, doesn't have any real solutions. Its discriminant is less than 0, so it's going to have complex, non-real solutions. Let's go ahead and write them down using the quadratic formula, which is negative b plus minus the square root of b squared, which is 1, minus 4ac, which is 12. 1 minus 12 is negative 11, and I can write it as square root of 11 times I. Using the imaginary unit, I can just write my non-real solutions. Make sense? So we got 4 u values. U equals 0, u equals 1, and u equals this number, or 2 solutions from here. So there's a total of 4 solutions, which kind of makes sense because we have a quartic equation. But that's not the end of the story, because these are u values. And how do we convert? We know that square root of x is equal to u, so we're going to set each u value to square root of x. So for example, if square root of x is equal to 0, this means x is equal to 0. If square root of x is equal to 1, this means x is equal to 1. And if square root of x is equal to, let's say, negative 1 plus square root of 11i over 2, then from here we can find x by squaring both sides. And if you square this, you're gonna get a non-real solution as well. And to keep a long story short, that is going to be negative 5 minus square root of 11i over 2. So far we got 3 solutions, and the fourth one is going to be coming from the conjugate of this complex number, and that is square root of x equals negative 1 minus square root of 11i over 2. And if you square both sides, you get negative 5. Obviously, if you square the conjugate of a complex number, you get the conjugate of the square of the original number. Okay, so squaring, or any power, basically preserves the conjugacy, if that's a word that I can use. Okay, great. So we got 4 solutions so far, and that's pretty much it. And so when the bases are the kind of relatable, like 3, 9, and 27, problem is kind of easy. Anyways, let's take a look at the graph real quick, and then we'll finish up. So for this one, I graphed y equals x squared plus 2x, which is a parabola, right? Obviously, it is a parabola that has roots at negative 2 and 0, as you can see here. And then the other one, y equals 3 times the square root of x, is a radical function. It's only defined for non-negative real numbers. So x is greater than or equal to 0. That's why you only see like kind of like a one branch, right? If you square both sides, you get y squared equals 3x, but that's just a parabola, which is sideways, but you only see one branch because x needs to be positive. All right, so there's another branch that you can kind of reflect. But anyways, this is basically the graph of these 2 functions, and they intersect at x equals 0 and x equals 1. As you can see here, if x is equal to 1, then y is equal to 3. And you're going to actually verify that if you replace x with 1 on both sides. If you think about the original problem, you're going to notice that it actually both values works, right? X equals 0 means 1 times 1 equals 1. X equals 1 means 3 times 9 equals 27. So that should kind of be obvious, but we still wanted to solve it, especially for the non-real complex solutions, right? And this brings us to the end of this video. Thank you for watching. I hope you enjoyed it. Please let me know. Don't forget to comment, like, and subscribe. I'll see you tomorrow with another video. Until then, be safe, take care, and bye-bye.